Greetings! So today we'll learn about a variant of the scheduling problem, scheduling, for the case of independent machines. Okay, now here we still have m machines, and for the input we have jobs to complete and we have to assign them into a machine. But right now we have a job is a tuple. So right now it's like the ith job is an m tuple, pi1, pi2, pi3, and so on till pim. Basically, so pij is the cost, say the time cost, so the cost of job I if we assign it to the jth machine. Jth machine. Of course, these are, well, non-negative real numbers. And still the load of the machine J is just the sum of the cost of those jobs, of which we have an assignment of the ith job to the jth machine. But right now we of course have to use the parameterized version of this cost, and still the make span is just the maximum of all the loads. And what I just forgot to write explicitly, but I mentioned it, is that this tau I is always an index of a machine. Okay, so that's it. Let's see an example. So for an example, if we have, say, 3 jobs, 3 machines, and we have an input sequence as follows. So first I will triple. Since m is 3, I have to describe a job by a triple, so it's 1, 2, 3. This means that if we assign this job to the first machine, then it will take 1 unit of time. If we assign it to the second machine, then it will take 2 units of time, and if we assign it to the third machine, then it takes 3 units of time, seconds, minutes, whatever. Now the second, let it be 5, 1, and 2. Now the third should be 4, 4, and 2, why not? And then we have the 3, 1, and 5, and then we have the 1, 2, 6, and of course we have the 6, 6, 5. Okay, now let's see what happens, for example, if we just schedule it to machines, say in a greedy way, like following. So if we assign each job, and this will be the first, this will be the second, and this will be the third machine, for now. So a greedy algorithm can make we just assign a job to the machine on which it has the smallest processing cost. So it's possible that I will assign this job to the first machine because it can be completed on that machine the fastest. So I just take this here, 1, 2, 3, And right now I'm trying to, well, so on this machine it will take 1 unit of time. Now if I assign this second job to the second machine, because it's done on the second machine the fastest, so it will still 1 to 5, 1 and 2. So right now the load of these machines, this guy has a load of 1, this guy has a load of 1, and this guy has a load of 0, because there are no jobs there. But for the 442, I will try to draw a larger rectangle, because it takes 2 units of time, and right now we have a load of 2 on the third machine as well. And then we have this 3, 1, 5. Since 1 is the smallest one, I can schedule it here, why not? 3, 1, and 5. And then this 1, 2, 6 is put here, 1, 2, 6, if we run this greedy algorithm. And then we have this 6, 6, 5, which should be put here, 6, 6, 5. I forgot to change the loads, so we have a load of 7, and this will be the make span in this case. Now it might be optimal and might not be optimal, so let's just try to make a better assignment. So for example, here we have this 6, 6, 5 triple. Now the 6, 6, 5 means that it doesn't matter where I put this job, it will cost at least 5. And this means that the optimal make span is at least 5. And in general, we have this bound that the optimal cost, which is still denoted as L star, is at least as large as the maximum possible minimum cost. Bij. We've seen these expressions quite a large number of times, but basically, so to schedule this job, we have to spend at least 1 unit of time. To schedule this guy, we have to spend at least 1. For scheduling this guy, we have to spend at least 2, and so on. And this guy has the maximum minimum value. Yeah, so in this case, this gives you a bound of 5. Also, if you just consider these rectangles, again, there is another general bound, which is just okay, so it comes from the fact that if I have this guy here as the make span for L star, even if this whole rectangle is filled with jobs, well, how large each job can be, but each job at least takes the width of the minimum possible width. In this case, we just each box exactly takes a space, a time of its minimum possible cost. So in this case, the total area of these rectangles, if we assign all the jobs, will be at least 1 plus 1 plus 1 plus 1 plus 2 plus 5, which is 4, 6, at least. So in general, it's just the sum of the minima of the Bij. For each job, I'm taking a rectangle having the area at least the minimum of Bij divided by m, because I can use 5 of these rectangles, so I can this is also a lower bound for the optimum. Now in this case, this is 1, 2, 3, 4, 6, 11 divided by 3 right now. Now here the 5 is a better lower bound, since this guy here is smaller than 4. So we know that the optimum for this particular input is at least 5, and actually we can do 5, because if we just try it, well, in order to reach the 5, I have to schedule this last job onto the last machine, because, well, otherwise it won't fit. So if I schedule this guy to the other machines, then it will have a cost of 6 already. But if I want to hit 5, then I have no other option than putting this guy there. And the other 5 jobs should be scheduled somehow to the other machines. Now, since this guy here is a 4 for 2, this means that one of the machines will take a load of 4 only to handle this job, because we can't use the third one. So basically this is here 1, this is here 1, this is here 1, and this is there 1, but this guy here is only 2, meaning so I have to pair this job with either this guy or with this guy, but because otherwise, if I'm using the second machine, which is possible, so if I'm just taking here the 5, 1, 2, and here the 4, 4, 2, then the loads will be 5 here because of this guy, 1 plus 4, which is 5 here as well. Now let me check whether we handled all these other guys. So 1, 2, 3 is okay because it's only 1. Cool, that's handled. And then I have this 3, 1, 5, 3, 1, 5. This is larger stuff, but it's done. And then we have this 1, 2, 6, which also has a cost of 1 on this machine, so the load is again 5, which means that we are able to make a schedule of cost 5. The optimum is 5 because we already know that the optimum is at least 5, and we also have a solution reaching that bound. So we have these 2 general bounds for the case of the scheduling problem for unrelated machines. Now the list algorithm, I just switch to green, so the list algorithm if we are just trying to schedule the ith job, we just compute load of the jth machine plus the scheduling cost of the ith job on the jth machine for each machine, j1 till m, and then we just choose the minimum, choose the j, minimizing this. Yeah, now that's great. Let's try to do this for this very same input. I'm not sure whether we still have some space, but I'm just making it because I don't want to copy the input. So right now I'm just erasing this part. This is scheduled by the greedy algorithm, and right now I don't want to use the greedy algorithm but the list algorithm because I know the competitive ratio of this list algorithm. Yeah, that's cool. So initially we have these loads. I should also erase these loads. So initially we have the loads for the machine as 0, 0, and 0. Now to schedule the first job 1, 2, 3, I just have to compute 0 plus 1, 0 plus 2, and 0 plus 3 and choose the minimum of these guys, which is of course 0 plus 1. So the job 1, 2, 3 will be scheduled here according to the list algorithm as well. Now that's fine. And at this point I have a load of 1 on the first machine as well. Now as I have a load of 1 on the first machine as well, to schedule the second job I just have to compare the 1 plus 5, the 0 plus 1 and the 0 plus 2, and here this 0 plus 1, which is only 1, will be the winner, so I will schedule this 5, 1, 2 to that machine. Now of course the load of this machine will be 1, will be 1. Right. Now on the third case I have to compare 1 plus 4, 0 plus 4 and 1 plus 4 and 0 plus 2, and in this case this 0 plus 2, which is 2, will be the minimum. So again the 4, 4, 2 will be scheduled here. This is not that different so far. And then the greedy algorithm's output. So right now the load on the third machine is 2. Cool. Now this 3, 1 and 5, I have to compare the 1 plus 3, the 1 plus 1 and the 2 plus 5, and in this case the 1 plus 1 is the minimum, so I will have to schedule the 3, 1, 5 onto this machine as well. And contrary what you might see here, this is again a load of 2, which is the same as the one on the third track, so it's great. Now to schedule the 1, 2, 6, 1, 2, 6, I'll have that 1 plus 1 is the least possible value, the minimum of these guys. So I again have to schedule the 1, 2, 6. Right, and finally, so the load will be 2 on this machine as well, and finally I just have to compare the 2 plus 6, the 2 plus 6 and the 2 plus 5, and so the 2 plus 5 will be the smallest, which means that I will have a scheduling exactly this, which is exactly the same as the one with the greedy algorithm. So in this case this is the same, but in general this is how you do it. You don't only take into account the jobs cost, but you just add the load so far on the machine and the processing cost of the job. So for example, if you just have these jobs of 1, 2, 1, 2, 1, 2, 1, 2 and so on, 2, whatever, on 2 machines, then the greedy algorithm would just use the first machine for each of these guys, and it would have a cost of 5 in that case. But for the least algorithm, you first use the 1, 2, that's fine, for the first machine. For the second, you will have a tie, so 1 plus 1 is the same as 0 plus 2, and in this case, as usual, you are just using the least index rule, so you are just okay. So this is the first one, but for the third one we will compare 2 plus 1 and 0 plus 2, and now this 0 plus 2 will be the definite winner, which means that you will put the 1, 2 there. And then you just repeat it, put the 1, 2 here, put the 1, 2 here, and should another 1, 2 arrive, that will be put here. So on this particular input sequence, the list algorithm performs better than the plain greedy algorithm. Now we are able to compute the competitive ratio of the list algorithm. There is a theorem for that, so we have a theorem. The theorem says that the list algorithm is exactly m-competitive. For the case of unrelated machines. Now, to prove this, we have to do two things. First, a lower bound. This is usually done by giving a bad input or a family of bad inputs. So for this we will give bad inputs. For the upper bound, we prove m-competitiveness for each possible input. So we prove L divided by L star as usual. So L will denote the value of the solution produced by the least algorithm, and L star is just the cost, the optimal cost. So this is at least M. Now, for the bad input part, we will do this following. For every possible epsilon, we will define an input on which the algorithm's cost divided by the optimal cost will be, well, it will be m divided by 1 plus epsilon, which means that and of course for each m, which means that if epsilon goes to 0, then this guy here will go with tend towards m, and that will prove our point. So in this case we are not only giving one input on which the ratio is exactly m, but we will give a family of inputs on which the ratio converges to m. But this is enough to show. Now let's try with the first one. So let's continue with the first one, giving a lower bound a bad enough input. So if we have m machines, then the only thing we have to do is just define a bad enough input. Now a bad enough input will start with a job of cost 1 plus epsilon. Remember, there is a parameter epsilon which you might think as 0.01 if you wish. And then on the second machine it would cost 1, and on all the other machines the processing of the first job would cost m. Now m is at least 2, of course, so in this case the least algorithm will just put this job there and it will have a cost of 1, right? Since this guy is the smallest possible. That's fine, but on the second job we will have the 1 plus epsilon here, we will have a 2 there, and in all the other coordinates I will use m's. M. Now in this case the least algorithm will, the least algorithm won't use the other machines because m is a large value. You can think of m being infinite if you wish, so it's just there for assigning a large enough cost not to use those machines. But here we just compare the 1 plus epsilon on the second machine and the 0 plus 2 on the third machine, and this is smaller than that. Since 2 is smaller than 2 plus epsilon, which means that the least algorithm will assign the second job to the third machine. Now comes the third job, which is just 1 plus epsilon. I'm pretty sure you will be able to detect the pattern. So there are only 2 coordinates with a non-m value. One of the coordinates will have the 1 plus epsilon and the other is just the index of the job. But in this case also, this is 2 plus 1 plus epsilon, which is 3 plus epsilon. But for this machine we have a sum of only 3, which means that the least algorithm will schedule this job to the fourth machine, and so on. And for the next one, we will have the 1 plus epsilon there and the 4 there, and m's. And it will be assigned there, and so on. Now for the last case, we will have, or the one before the last, the penultimate case, we will have the 1 plus epsilon m minus 1 will be, if you just drew this here, the m minus 1th job will have the position of the 1 plus epsilon there, and it will be scheduled here, m minus 1, and then the last job will have the 1 plus epsilon on the last coordinate, and all the other guys will have a cost of m. Now here this m is important to have this m. The others can be infinite distribution, which will be used here, so it will process on the mth machine. You can just verify that the released algorithm actually produces this schedule, and the cost of this guy is m. While the optimal cost, I'm pretty sure you can see it now, the optimal cost is just to put the ith job to the ith machine. So if you just use these guys, the optimal cost will be 1 plus epsilon, which means that L divided by L star is indeed M divided by 1 plus epsilon. So that's why we have a lower bound of M, because if epsilon is small enough, then this ratio is almost M, and we can approach M as close we wish, so it's done. So for the lower bound we are done. Now for the upper bound, we will prove that L divided by L star is at most M for any possible input. Now for this we will use induction. So for each sigma we will have that the L divided by the L star is L at most M is done by induction. By induction, and it's induction on I, on the number of jobs, say, on I. So we will show that after processing the first I jobs, the load of each machine will be at most the sum of the minimum costs. Yeah. So after processing the first I jobs, the load of the jth machine will be at most the sum of the minimum costs. Bij, well, I should not use, okay, so let's use this j prime, so the minimum possible costs for each the first I jobs, I prime jobs. Okay, so I goes from 1 till I prime. Yeah, that's great. This will be proved. Now, what does it mean? It means that, so for example, in our first input, this means that after processing the first input, the load on each machine will be at most 1. After processing the second, we will have that the load of each machine is at most 2, because we are just summing the minima here. After the first step, the load of each machine will be at most 4, because 1 plus 1 plus 2 is 4. And then we will have a load is at most 5 if we run the list algorithm, and then then it will increase by the next minimum. It will be at most 6, and then the load will be at most 13. 6 plus 5 is 11. Yeah, exactly here. And if you just remember back, we also have another bound of this. The sum of the minimum divided by m is a lower bound for L. So if we manage to show this, then we will have at the end the load, each load is at most the sum of for all the jobs of the minima Pij. And if each load is at most this value, then their maximum, the max span, is also at most this value. This is at most this guy. And I also have that if I just divide it by m, then it will be at most L star. Okay, I just divide it by m as well. So this is coming from the induction hypothesis, and we divide it by m, and this is coming from the general bound. And this guy here, L divided by m, is at most L star, is the same if I'm just multiply it by m and divide by L star, is the same as L divided by L star is at most m. So if we manage to prove this, then we have the upper bounds. So the load of each machine is at most the sum of the minima of the costs of the jobs so far. Now we can do this by induction. So if I is 0, then it's clear that each load is 0, and that sum of the minima so far is again 0, because there is an empty sum, so it's fine. 0 is at most 0. Now assume the formula holds for I, and let's move to I plus 1. Okay, so let say L be the index of the machine, minimizing the I plus 1 jobs L. So this is just the index of the machine on which the next job would cost the least possible value. So then on that machine, the new load would be what? It will be the load of the F machine originally plus Pi plus 1 L. Now by the induction hypothesis, the F machine's load is at most the sum of the, say, I'm moving this sum from say I prime from n from 1 till I. I'm trying just to 1 till I. This is just the minimum of the Pi prime j plus this guy here, pi plus 1l, since l is the one minimizing the jobs cost, current jobs cost, this is the same as the minimum of these guys. Yeah. So L is just defined to be the j for which pi plus 1j is the minimum. So this is the same. And this means that here we have the sum moving from 1 till I plus 1, since I am just summing the minima and again the minima for I plus 1. I'm just including this guy there, and this is just the sum of all the minima from 1 till I plus 1, which means that on that machine the new load would be at most this expression. Now we are choosing, the list chooses the minimum of these sums, which means that the machine onto which the list algorithm assigns this job, it will have a load plus new load, which means the new load will be at most this expression. So the machine onto which list actually schedules the I plus 1 job will have a load smaller than the sum of the minima. Of course, say it's I prime goes from 1 till I, and the minimum goes on all over machines, so this is fine. And on the other machines the load is not changed, so on the other machines load doesn't change. Which means that their load is at most the sum from I prime going from 1 till I by the induction hypothesis. It's just I prime going from 1 till I, the minimum of this pi prime j's by the induction hypothesis. And since we have non-negative costs always, it's at most the sum. We just add the new jobs cost, so we are moving to 1 I plus 1 and just sum the minima of this pi prime j's till I plus 1. So we have this bound for all the machines, including the one onto which the job is actually scheduled, and for the others as well, which means that we just proved this thing. And from this, if we just process all the jobs, we can deduce this bound for the competitive ratio as well. So basically that's what we should know from the unrelated variant of the scheduling problem. Next time we will see another variant where each machine will have a constant speed, and they will just be faster than the other machines by this speed factor, but we will see it just later. Till then, bye bye.